right, doing this problem called word break. I think I've done it in the past. Let's try and do it again. Given a string as in a dictionary of strings word dictionary, return true if s can be segmented into a space separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in segmentation. Let's understand what it means. So a string as is LeetCode, word dictionary is leet and code. Output true, return true because LeetCode can be segmented as leet and code. Okay. So another example, apple, pan, apple. There is a word dictionary called apple and pan. So yes, you can divide it into apple, pan, and apple. Return true because apple, pan, apple can be segmented as apple, pan, apple. Okay. Another example, cats and dog. So the dictionary is cats, dog, sand, and cat. Okay, this is false because now this is interesting, and this is where you see the complexity of the problem maybe. So cats is present, so you take cats, and then you could have also tried, let's say cat is also there, right? So you could try with cat as well as cats, right? So if I try with cats, then I use and then just OG is remaining, or I can use cat and then I can use sand and then OG is still remaining. So right, so that's the thing. So let's look at some constants as well. As well, learn this. Okay, all lowercase English characters. Word dictionary of I.len. That means what? Every word is not, there is no word which is more than 20 letters long. So the length of the word is not that big. Total number of words in the dictionary is also not that big. But when we look at it, essentially we have to find if a word is present in a dictionary, right? And one of the ways to do that would be save the dictionary as a hash set, and then you can always check, hey, is CA present in the dictionary? And you'll say no. Then you'll check, hey, is CAT present in the dictionary? And you'll say, yeah, it is. And so then, uh, you would try that option once, right? So you'll try CAT. So can I just do using a hash set? Um, I mean, looks fine to me. So I maintain the lists of words in a hash set. Okay, let's come to a whiteboard to come to first a solution, or like a possible approach that we'd use. So I'm using this example called CATSAND, cats and OG, right? And obviously, if a word has to be broken down into strings, I'll maintain all my words in a hash in a in a hash set. So I have cats as one, dog as another, sand is another, and and is another, and cat is another, right? These are different words that are present and can be considered as full words. Now, the first thing to note is uh, the query to uh, check if a word exists, right, in a hash set. It's not really O of one. It's actually O of the word length, right? Because it has to first generate the hash set from that word, and so that means it has to at least traverse the word. Like that's the bit we sometimes ignore or miss. That querying something from a hash, especially if it's a string, then to generate that hash code, it it would have to go through the each and every um, the query has to be, you have to understand this, the query is O of word length and not really O of something else, right? But we know that the word length is limited, and maybe that's something that we could use, that the word length is limited by 20, right? So in that sense, okay, uh, it maximum O of 20, which is still sort of constant. But okay, that's one thing to note. Now the approach that we are saying is this: I will start from C, and then till I find a match, I will continue. So for example, C is not present in the dictionary, CA is not present in the dictionary, CAT is present in the dictionary. But now, you know, that's causing too many like the lookups, right? So when you check, hey, C is present, CA is present, CAT is present. Individually, for each of them, it has to build that hash code again and again and again, right? And then you will check CATS is present. And so basically what I'm trying to come at, and this is something that I recall from past, is that looking for words in a dictionary, try is a better data structure, right? So because I tried a better data structure, because if you have already checked for CA, then to check for CAT, that does not take much time. That's the main bit that you need to understand. Okay. But okay, we'll come to try. But let's first build a solution, and then okay, the data structure that we save the dictionary in or the lookup, instead of using a hash set, we use a try. That is something that we can do. That's fine. But first, let's build a solution. So the solution is again the same. That for each prefix, essentially, we get here. We go to CAT and we find out that CAT is present in the dictionary. So then we'll check whether this remaining bit can be divided or not. So yes or no, right? So something like uh, word break of string starting from index. You what you have to do this here is if you find you find different words. So index to k for each index to k uh, in dictionary. You check if you can do word break properly on k plus 1 to and that sort of a thing, right? So what that means is when you do cat, and now you're solving for sandy dog, and if you find something in sandy dog, then you will return, yeah, finally I was able to break, right? So in sandy dog you would do as a and d, so you'll find, hey, this works. And then OG you will try and you'll find nothing, it does not work. So this does not yield any result. Then you would then check Sando, that wouldn't work. Then you'll check Sandog, that wouldn't work, and so on and so on. So let's first write a code based on a hash set, and then we'll see and improve based on try. All right. All right. So coming back to code, coming back to uh, hash set of string. Let's call it set equals to new hash set of, okay, a new hash set, and I'm going to do for each word in a word dictionary, uh, add it into a set. So set.add word, and you want to do is return word break as word. You're going to pass in this set, and you're going to pass in the current index, which is 0, and then you do boolean word break string as a hash set of string called set and an integer index. And now here what you're going to do is um, for int r equals to index, r is less than s dot length r plus plus, if set dot contains s dot. All right, let's fix the spelling of contains. If the set contains s dot substring starting from index, I think it's left and right plus one, right? So right plus one will be r plus one, lr plus one. If set contains this, uh, and the word break for the next, and the next part you can break. So if the set contains this and word break s comma set comma r plus one, from r plus one onwards, if you can make another break, then that's great. Then you return true essentially. And if you are here, then you return false. Now one more thing, which is you might reach the end of your string, which is if r equals to uh, s dot length. In this case also you'd want to return true, right? So this is fair, not r actually, the index. If you're looking to break, yeah. This is correct. This is fine. Otherwise, request to this and yeah, all good. So now the problem obviously here is that this loop and then when you do set dot contains looks like often, but set dot contains again multiple times substring and then calling it like we said to generate the hash code often internally. So calling or becoming overall and square is a problem. Let's run first of all to even see with a small test cases that it even work or not. Seems to work. Let's submit and see if it throws a time limit exceeded or it accepts the solution. It does throw a time limit exceeded. All right, for a word for a big input like this, you can we can figure out right these many different. So A would exist, A would exist, A would exist, and we could keep on generating hash codes and stuff. So this is where the try would help. So first, let's again understand the try data structure, right? Yeah, I also have to refresh. So let's do this separate problem called implement try. Let's understand that, and based on that, we'll update our solution for the word break as well. All right. So what's a try? A try, pronounced as try, or a prefix tree, is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. Implement the try class. So you have to initialize the try object. You have to do void insert string word, insert the string word into the tree. Boolean search string word return true if the string word is in the tree, and Boolean starts with. So you have to do all of these. So what's the general idea of a try? Let me recall, otherwise we'll have a read in one of the articles. So coming to whiteboard, let's try to recall what a try data structure looks like. Oops. I think it depends upon, first of all, your alphabet, right? So for every, basically you maintain a, like it says, prefix tree. So there are a few indicators. One of them is you want to maintain somehow end of word. I'm trying to recall. So one of the things that you want to maintain is end of word. And how do you actually represent is something like so you to start with your first character can be uh, let's say a simple case where you only can have three characters A, B, and C. I'm taking a simple example, a small alphabet which just only contains A, B, and C. So now how to represent dictionary in a try format would be uh, like this. So this corresponds to A, this corresponds to B, this corresponds to C, right? Now, so you have essentially an array of this size. So you have a try node, right? So you got your try node, and what this try node contains is an uh, array of try nodes. So this contains essentially a try node array of length, the alphabet size, right? So what this means is that I'll come to everything. So this is what it contains. And another thing it might also tell you is, hey, am I and of word or not? Right? These are the two things that it can contain. And you can have your root. You can have your root node. So your root, yes, or you can have a root node also. It's like this. So essentially, what it means is that um, so this node corresponds to A. This corresponds to B. This corresponds to C. Right now, let's say you can let's say different words. One of the words is A B, another word is A C, another word is A C B C B A. Right? These are the three words in your dictionary. Let's imagine, or let's take another one, C A B B C. Right? These are the four words in your dictionary, and but you can see there are only three characters, A B and C. So to start with, let's add A B into the try. So what that means is uh, A B into the try means is that I have, so initially I have this root node, right, which says, can I have A, can I have B, can I have C, right? I have this root node, and now you can have A. So for A, create another node. So for A, so essentially what it means is that I have a node which has the array of nodes, right? So this is my array of nodes in my root node, right? Root node is an array of nodes, and initially all of them will set to null. So this is null, this is null, this is null. That null will indicate that you can't have a character starting from like at this position you can't have this character. So starting from this is corresponding to A, this is corresponding to B, this is corresponding to C. So from A, you when you create another just like another node, that tells you that okay, A exists, right? And then when you add B, that means B corresponds to this, so you add a node corresponding to B, like this node, right? And for this node you also you say here, you say, like, for and of word, let me make it a red, so that says this is and of word, right? So and of, or maybe just make the node as and of word. So this node is and of word, right? This B, which has a list of array, and the blue dots represent null. Okay, so this means, so I have to check A and B exists. That's the way. Now let's add A and C. So for A and C, you will do, and this is also a complete word as well. So you'll do, okay. So you'll mark the and of word, and C also exists. So you'll also create like an array for C, right? So this is how you know A B exists. This is how you know A C exists. The next is A C B C B A, this big word. So from A to C already exists, that we already know. A exists, we already know. C exists. Now in C, you want to have make A exist, so you add a node here. And from A, so now you got what? A C. Okay, it's A C B. That's to undo, 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 undo. Okay, this is AB. We know AC exists, and no, we don't know AC. Okay, to make AC exist, we had to add this. Okay, so now you know AC also exists. This is ABC. Anything. So we know AC exists, and then B. So ACB exists, and then ACBC exists. You get the idea, right? And then ACBCB exists, and then A exists, right? So that's you can track. So A, C, B, C, B, and A, right? That's the gist of it. So that's the representation. Let's come to code and see if that becomes more clear from there on out. So coming to code, so you are defining a try, and then you are doing. So let me define a node, a try node. So a class try node. What it has is a boolean which says end of word. So you can tell here this is a word. You can also search for full words or prefix both, and you have a try. So here, what is the alphabet size? Lowercase English characters. Okay, so try node array. Uh, call it what? Just call it next equals to new try node array of length 26, and you will initialize this to false, right? This is your node. Now, when you're initializing a try, you would want to initialize like a root node, right? So let's initialize a root node. So in try, let's maintain a try node called root, which is null, and here is what you do: root equals to new try node. So now in root, it has an array of nodes, and all of those nodes are null. That means that you cannot, so far, you cannot start with any character, right? And now you start adding words. Okay, go down. So now you start adding words. How do I add a word? Let's think. So the way to add a word would be I go through the word character by character, and I'll keep adding my nodes or updating my nodes, right? And updating my end of word flag and so on. So for each char, so first we'll do try node equals to root. Then we'll do for each char c in word dot char array. So we're going to character by character, and we check if the node exists or not. So if node dot next of okay, node dot next is the array, right? So if node dot next of c minus a, if it is null, that means you have to add first of all. So node dot next of c minus a equals to new try node. That's one thing, and then you move to the next node, right? Node equals node dot next. So you do, and that you have to do regardless, right? So either it exists or it doesn't exist. So if it exists, if it didn't exist, then you create. If it exists, then also it's fine. So node equals to node dot next of that specific character. So now you are at the node corresponding to that specific character. And now at the end of this thing, at the end of it, you will be on the last character, node corresponding to the last character. So you do node dot end of word equals to true. All right. So that makes sense to me. Now let's do search. Okay, so for search again, we do start with the root node. So try node equals to root, and then we do, let's do here I equals to 0, I less than, or can I continue with these? Let's see. For each character C in word, for each character, you do this. If node dot next of node dot next of character minus, if this guy is null, then you return false, right? That means it doesn't exist. Otherwise, you do node equals to node dot next of C minus A. So at the end of it, either you would have returned null or you would be on the last node. So now you want to return if this last node is an AND word or not, right? And the other is starts with. That means the same as this, right? Except that it may not necessarily has to be an AND word. That means everything exists. So here, if you're able to reach the prefix, then just return true. Okay, so that's the thing. Now let's run. Uh, what's the problem? Cannot find symbol word dot to character. I think small t and small t. Okay, run. All right, fix more stuff. Is end of word and end of word. So there is no is end of word. Return no dot end of word. Okay, just what we named it. Fix more stuff. Okay, try node end of word looks like this, and so fix that. Run. My goodness. Okay, here it's calling him prefix, so change it to prefix, and that's fine. Run. Accept it. Submit. And this works. This is how a try works. Let's quickly talk about the search, right? Let's quickly talk about the time complexity of doing a search. So the time complexity of doing a search would be essentially the size of the string, right? The same. So it is the same as it is the same as hashed in that sense. But if I am maintaining the context, meaning that if I've already searched for a prefix and then I'm searching for a prefix plus one, then it will be O of one, right? So I don't create the same substring again. I maintain this. So I don't do like a fresh search from start. But if I have searched for like ABC and then I'm searching for ABCD, I would maintain the context whether ABC exists or not, which is where the try might help, right? So let's come here. And what I meant by that is now let's convert this logic into using a try. So we don't use a hash set, uh, and we build. So first we build a try, right? Could I copy the code over from here or what? Let's copy some of the code. So let's do this. So let's call this. So let's call a function called. Uh, no, let's use the exact same thing. Why not? Like we built a nice little thing. So let's just use it as is. Okay, if you say so. But I feel like we will not use this search, right? We will have to explicitly do the search to avoid multiple stuff. But at least let's build, right? Something will be useful still. Okay, let's copy everything, go there and go there. So I copy the code entire thing. Now I do word break. So what I'm gonna do is uh, build a try. So try equals to new try, and then I'm gonna do for each string word in. So hold on. Yeah, fine. Word dot word dictionary. I'm gonna do try dot. What exactly does it say? Try dot insert. So I am going to insert the word. right? And this is not gonna happen. Okay, and now let's think about it how to optimally do this search, right? The contains search, and this is where I don't think I think I have to pass the current try node corresponding to the current position. So I maybe return here. Let me think. Yeah, I return I pass try dot whatever the root node is of the try, which is um, root. Okay, so try dot is it public? We'll see. We'll fix that if it's not. So try dot root. This is what we pass, and here we'll do try node of uh, just node. Yeah, just call it node. Okay. So we're not passing the hash sat. Let's remove the hash sat. Let's remove the hash sat. Now, obviously, this is one case, which is all good. Now, what we want to check is we have the index, and so for each integer index starting from this point, we are going till the end of the string, and we are checking. Uh, this is a tricky bit, right? This is definitely the tricky bit. So let's remove this and let's see what we exactly want to do. So I want to check if this is a complete word or not, right? And I can break early if it's not a complete word. That's not the benefit of it, right? That's not the definite benefit of it. Like if a b is not present in the dictionary as a prefix, then you are not going to find a complete word as well. So definitely improves the efficiency in that sense. So you're gonna as soon as you move across, as you move along the word, you're also going to. So okay, so let's do char c equals to s dot char at index, right? And now we want to check is if at any point if you see if node dot next of c minus a, if this is null, that means you can just stop right here, return false, right? And else, okay, what's the else? So else, I have it. That means it exists. There are two cases here. If it exists, what is one case? If it is a full word or not, right? So if it is a full word, if node dot next of c minus a equals to no, so let's do this. Else you definitely move to the next. So node equals to node dot next of c minus a, right? That's clear. Now if node dot what it's called end of word, yeah, if node dot end of word, then you can try then you can try and you're able to find a combination. So if node dot end of word and word break of s starting from, so this is one word, so starting from index plus one, and this is the Yeah, this is a node. Is it the right node? Yeah, the parent node, right? And I have to look it's in its child to see if there is a yeah, this is correct. So if this happens, then you return true. Otherwise, you just move to the next node and you will continue looking. Uh, okay, let's run. Cannot find symbol. Try node. It doesn't understand what a try node is. I'll tell you what try node is. Try node is try dot try node. That's what try node is because I guess try node is defined within try. Is it? Yeah. You could also do like this. That is fine. You could also do it outside, and then you can avoid this issue. Okay, that's done. And compilation error fix. Okay, this is a minor one. Let's fix more. All right, so no more compilation errors, but you're getting a wrong answer though. All right, let's see. So why are we getting a wrong answer? So first we built a try. Let's quickly see. Obviously that has been validated. So adding your uh, adding your nodes in the try should not have any problem. That should just work. And now try dot root is what you're returning. Word break. If you have reached the if basically this is the base case where if your string is empty, okay. At the end, that means if you reach the end of your string, that means everything is awesome. You just return true, and then now what you're doing is from starting point index to the oh okay so okay, c equals to caret this has to be r. Okay, run, and usually a wrong answer. So continue. Okay, so you get the character at the starting point, and you check whether that character. I think there is a wrong. There is something that you're missing. No, no, no. It's correct. So we check whether this character exists or not. If it does not exist, then that means you just can't break. There is no way to break, which is fair. Otherwise, you get the node, corresponding node, right? And if this node is end of word, that means this is a word, and from index plus one there is another word that you have to check. And for the index plus one, that's the thing. For index plus one, this okay, index plus one, you have to again start look from the beginning of the dictionary. So you don't have to pass this. You do here try node equals to root, and that's it, right? And because again you're looking for a fresh word. Okay, run. I think I passed it from somewhere else as well. Fix that. All right, run. Fix more things, but he doesn't know what a try is. Like he doesn't know about this guy. So what do I do? Put it out. Put it here. Okay. Fine. All right. Still getting wrong answers, man. Still getting wrong answers. Okay, let's go back. So now I initialize my node as the start root node, and then I check for that's the example here is LeetCode. So I check L. Okay, so yeah, so I check obviously for L node will exist, so I go to the next one. Node is end of word, not true. Yeah, so in case of node is not and over, what am I doing? I am going to the next R, looking at it, checking for E, checking for E, checking for T. T is end of word. So then I call word break and I start from C. It should have worked. I don't know why it did not. Uh, all right, let's see. LeetCode. Hmm. Let's see how long we go till, right? So let's try and do some debugging. Um, let's keep printing this R or this character. No, let's see where we stopped, right? So for LeetCode, we do LEET, and then the next thing that it prints is E. Why does it print E? Okay, let's do this. Let's print if this ever happens. Oh man, the problem is I think you it's just a silly thing. Okay, I think it will work now. This index was a bit confusing. Yeah, okay. Seems like it might do a TLE, and it did do a TLE. But 35 test cases passed. Alright, this is the test case that fails. So word dictionary, and these are different words in the dictionary. And now, what am I doing? Inserting into the try is something that we cannot avoid. So can't optimize on that. There are some optimizations I do feel that might come from this, which is some repeated work, some DP. Can it happen? Oh yeah, it definitely can happen, right? So why don't you cache that? So let's because what I mean by that is you can imagine here, right? You can reach to this point and consider this as an AND of word in multiple ways. And if you have solved this, and then if you have solved this, then you wouldn't want to solve this again, right? Definitely there are repeated works. So let's cache that result. So let's maintain like a hash set of um, sorry, a hash map where you'll do. I don't even actually need to maintain like a hash map. I could maintain just an array. Okay, so a boolean array, would it work? False, true. We maintain an integer array. So an integer array with a value as -1 to initialize, right? So integer array word break, integer array cache or DP. So I'll do DP equals to new int of DP equals to new int. What's the size? Size is word dot length. So as dot length, and I will initialize it to -1. Now if you are ever get a call, and if, okay, so you don't wanna, you wanna keep this, but if dp of I is not equals to -1, then if it's true, then it will be 1, otherwise 0, right? That's maintained like this. And otherwise, whenever you're returning, before returning, just do, what is this I, man? Come on, index. So index dp index equals to dp of equals to 0, and this is where you make dp of index as 1, and here we can save it as 0 again. And let's try and submit if dp helps improve the time complexity or not. And it does. Beats 99%. All right, finally.